Hello and welcome to what would have been lecture 20 on April 2nd, 2020. In real life, you would have walked in listening to this. This is Evanescence, the album is The Open Door, and the song, once it kicks in, is Lithium, and I picked it because, well, we're talking about, among other things, metallic solids today, and this is a song whose title is A Metallic Element. All right, so we're going to talking about we're still talking about solids and liquids, so sections 10.1, 10.5, and 10.6 from the book. All right, there are just 3 videos today, and one of them is really short. So by the time you're done with these, you should be able to talk about the 4 types of crystalline solids and the intermolecular forces that are present in each, and also identify what type of solid a particular compound is based on its physical properties, melting points, whether it conducts electricity, stuff like that. So let's get to it. To start with, we're going to give you a quick breakdown of the main differences between solids, liquids, and gases. Now, we've talked explicitly about a lot of these guys. So let's one of the big things, how they deal with shape. So gases have no fixed shape, and they take the shape of their container and they completely fill it. Liquids, likewise, do not have a fixed shape, but they have their own volume. So they will not fill the container if the container is bigger than the volume of the liquid. Now, solids maintain their own fixed shape. They are not set by their container, and they remain rigid. On the molecular level, this is because on a solid, the particles are fixed in place in a very regular order. They might vibrate back and forth around a position, but that's it. They are not compressible. You take a piece of iron and you can squeeze down on it as much as you want. The iron is not, the volume of that chunk of iron is not changing very much at all, unlike gas. And finally, there is very little free space between particles. Now remember, this is also the same thing with liquids. There's a little more space on average, but not that much, and compared to gases where the spacing is 1,000 times the size of the particles themselves. For those of you that like to break things up into 2 types, there are 2 types of solids, amorphous and crystalline. So amorphous solids, so they are formed when generally you form solids by letting a liquid cool down. If the cooling occurs quickly, the particles solidify in not the most ordered state they could. This is like carefully placing clothes back in your drawers, or just shoving them in there. One of them is going to give you better looking piles than the other. And the amorphous is analogous to just when you shove them in there as fast as you can. Now, because of this, the particles end up being a bit more randomly arranged than they otherwise would be. But again, somewhat. These are still solids. And they tend to lack a regular form. So what happens is that there are small regions of these solids where they are lined up to where they're supposed to be, but the regions don't line up very well with the other regions. So there's little long-term order in the solid. Crystalline solids are pretty much the exact opposite. So this is, again, with the same compound, you could make an amorphous solid or a crystalline solid. The difference being how slowly you let it cool down. So when the liquid cools down and solidifies slowly, all of the little areas tend to adopt the same order. They line up. So there is long-range order over the entire chunk of stuff, no matter how big or how small it is. And it turns out that most solids are of this type. And again, as long as you let them cool down slowly enough. There is a small number of solids that no matter what will form amorphous. But crystallines are by far the most likely, and this results in very symmetrical arrangement of the actual edges of the physical piece of stuff. So this is an example of how regular an array is. So this is a electron microscope picture of a piece of gold. And each little dimple here represents an atom. And you can clearly see how regularly they are arranged. You can, if you look carefully enough, you can kind of see that these are rows that are somewhat staggered. The other thing that I want you to be aware of is the actual shape to look at in here. And it's not so obvious, I think, unless I draw it, is this is a repeating array of hexagons with one atom in the middle. This is something called hexagonal closest packing, and it is one of the most efficient ways of arranging round or spherical things. But the other thing I want you to get out from there is clearly that there is, a very, very regular order to this entire piece of stuff. So crystalline solids are composed of a repeating three-dimensional array of particles. And that particle has a name. I think we've actually talked about it in class before. It's called a lattice or a crystal lattice. Now, atoms, molecules, ions, whatever the substance happens to be, tends to pack together in a way that maximizes the attractive interactions between the individual ions, molecules, or atoms, and bonding interactions, and minimizes any repulsive interactions if there are any present. The shape or the order that is imposed on the molecular scale by this, you want to maximize the attractive interactions and minimize repulsive interactions. The shape that does that on the microscopic scale will actually affect shape on the macroscopic scale as well. Which is why you see a lot of hexagons in nature. So I talked about that hexagonal closest packing. So this is the shape that will make the most efficient use of the building material for this wasp's nest. You see it in pineapples, fish eyes, and on, let's say, human constructed things. This is the most efficient way to use wire to make a fence, or it is one of the most efficient ways. And it's also the most efficient way to get, again, any round thing laid down on a flat surface or a circular surface. Again, you can see this pattern is a whole bunch of dots that form a hexagon with one in the middle, and you can see it here as well. When explaining this, and if you have a slow weekend and you want to practice your geometry, you can actually figure out that this arrangement, this hexagonal packing, is the way that it maximizes the ratio of stuff to empty space in between them. And Martin Vallow was his name, and he proposed that drinks, or canned drinks in particular, should be sold in 7-packs rather than 6-packs, because that would be a more efficient way to pack them, because you don't care about the empty space in between the cans, you care about what's in the cans and what you can sell it for. And went through the geometry and found out that, yeah, the ratio of empty space to filled space is a lot smaller in this arrangement than the classic 6-pack arrangement. But then he said that his entire idea all fell down when he realized that he had to get that hexagonal package of beverages in a rectangular truck and drive it down a linear highway, so he kind of gave up on that. If any of you have worked in a grocery store stacking round or roundish things, you have actually inadvertently done this yourself. people that know how to do this, or actually if you just sort of tap them the right way, find out that there actually is a way to stack round or roundish things that minimizes the empty space, so it maximizes how many oranges or apples you can actually put out on your shelf. And what you find is that the key is to not put them directly on top of each other. And you can kind of see this clearly that the bottom layer, they're actually kind of lined up on a square grid. The second layer, you have actually placed them in the gaps in between the two. Because obviously if you put them right on top of the first layer, you would have a problem in that, well, they would fall right off. So you put the, layer 2, you put in the gaps between layer 1, and this way they A, don't fall off, and B, take up some of that empty space. Now what is not so obvious here is that the items in the third layer are actually not, you might think that they are directly above a item in the first layer, but they actually aren't. Not if you want to pack it as efficiently as possible. And it isn't until, so these are actually on a different grid than these, which are on a different grid than these. And it isn't until you get into the fourth layer that one of these is directly on top of one of the items in the first layer. So each of these 3 layers are different, and then they repeat 1, 2, 3, 1, 2, 3 until you get to the top of your pile of oranges or apples. All right, that's it for the first video, and we will see you on the second one.